Okay, so today we're going to talk about 6b on orthonormal bases. Okay, so the point is that an orthonormal basis will be like a really nice basis. That's the point. And the idea is that there's a lot of nice things that you can do with vectors when they're orthogonal rather than when they're not, right? So the standard basis of Rn, let's say of R2, consisting of this vector and this vector, there's other bases of R2, right? Like you could take this vector and this vector. But the fact that in the standard basis, these bases are perpendicular is really nice for a lot of reasons. If you move in the direction of one basis vector, then you're not changing at all the direction you're moving in the other basis vector in some way, right? So I'm being a little bit vague here, but orthogonal, the standard basis, one thing that makes it nice, let's say E1 up through En of Rn, consists of orthogonal vectors. Right? Because if you take the inner product, the dot product of these two vectors here, you of course get 0. Right? So every pair of vectors in the standard basis of Rn is orthogonal. That's nice. Actually, they satisfy an even stronger property, which is not only are the vectors orthogonal to one another, but also if you take the inner product with itself, you get 1. In other words, also they have unit length, right? Also, they all have length 1. So this strong property of being a set of orthogonal vectors that also has norm 1 is what we'll call an orthonormal list. So a list of vectors is called orthonormal. And so the ortho refers to like the orthogonal part. The normal refers to the fact that they have unit length. If each vector in the list has norm 1, and is orthogonal to all the other vectors in the list. Right, in other words, the list E1 through En is orthonormal if when you take the inner product of two of these vectors, if they're different vectors, you get 0. If it's the same vector, EI, inner product of EI should be the square of the norm. So that should just be 1. Okay, so notice here that throughout this course and just in general, I tend to use the letters EI to denote the standard basis of Rn. But in this section of your textbook, they use E1 up through En just for any orthonormal list of vectors. So since I like to stick with your book terminology, I guess from now on, if I use the letters E1 through En, I don't necessarily mean the standard basis vectors of Rn. On the other hand, it's not so bad because, as we just said, the standard basis is an orthonormal list of vectors, right? So anything that we wrote about the standard basis before, many of those things will still be true for any orthonormal list. So in principle, it shouldn't actually be that confusing. Right, so as we said, the prototypical example is the standard basis of Fn. That's an orthonormal list of vectors. But that's not the only possible orthonormal list of vectors. Here's an example. So let's take a list of vectors in F4. Let's take 1/2, 1/2, 1/2, 1/2, and then put 2 minus signs on the last two. Then alternate plus and minus signs, and then put minus signs on the middle two. Okay, so it turns out that this is an orthonormal. It's even a basis of f to the fourth. Okay, of course, it will be I mean, we can check that it's a basis by computation. There's sort of a lot of things to check here, right? I would need to check, I guess, in principle, 16 inner products. Well, some of them, you just switch the order of the vectors, so it's less than 16. I guess it's 4 times 3, it's 12. But you can just check, right? So the inner product of that first vector with itself, and this computation will be the same for all of the vectors. Right, so you can pull this 1/2 out and this 1/2 out. You have to take the complex conjugate, but it's a real number, so that's fine. And then, of course, this inner product in the middle, that's 4. That's 1 plus 1 plus 1 plus 1. And of course, that computation will work the same if you take any of the vectors with itself, because the square of -1 is also 1. And then, I don't know, let's just take the first two vectors to make sure that they're orthogonal. Again, you could pull out the 1/4. Of course, in the end, we're going to get a 0 anyway. But the point is that you'll get 2 1s and 2 -1s. So that'll be 0. And actually, if you take the inner product of any two of these vectors, well, you'll get 2 1s and 2 -1s. I mean, any distinct vectors. And so you'll get an orthonormal list. Okay, so the standard basis is not the only basis of Fn that is orthonormal. It's just the one that we're most familiar with. Right? But of course, it's not the only one because, yeah, I mean, even in R2, you could just draw a picture, right? You just take this vector with length 1 and this vector with length 1, and you'll get an orthonormal basis. And this basis here is sort of the analog of that one. Okay. And like I said, the point is that orthonormal bases are very, very, very nice bases. Okay, so we're going to see that today. So the first result is if E1 through EM is an orthonormal list in V. So I'm not assuming basis yet. I'm just saying any orthonormal list. Then it's very easy to compute the norm of a linear combination of orthonormal vectors. This norm is just, okay, well, if you square it, you just get the square of the absolute values of the coefficients. This is for all choices of scalars. Right, so this fact, of course, we know if you take the standard basis of Rn, then the length of a vector squared, you just take each of the components, you square them, you add them together, and then you take the square root, right? That's like a Euclidean distance. But actually, that only requires you to take an orthonormal list of vectors, not necessarily the standard basis vectors. Okay, so the proof is basically just the Pythagorean theorem applied several times. So I guess probably the Pythagorean theorem plus induction or something. But let's do just the case, and let's just suppose that m equals 3 for illustration. Okay, but the point is that A1, E1 is orthogonal to A2, E2 plus A3, E3. Because if you take the inner product of these two things, we know that you can break up inner products over a sum in either slot. And then you can pull out scalars if you want. From the first slot, you can just pull them out. From the second slot, you have to take the complex conjugate. Let's just do the whole dang thing because inner products are new. But now, right, I'm currently assuming that the E1 through EM is an orthonormal list, which means that these two inner products that I've written down here are 0. So this is just 0. In other words, if you take any linear combination of, in the general case, of E2 up through EM, it will be orthogonal to A1, E1, which means that by the Pythagorean theorem, the norm of this linear combination squared is just the norm of the first one squared plus the norm of the second one squared. But now you just apply the Pythagorean theorem again because A2, E2 and A3, E3 are also orthogonal. And so that norm you can break up, well, that squared norm. You can break up like this. And then now we know that you can pull out scalars out of a norm, except you have to take their absolute value when you pull a scalar out of a norm, right? So this becomes A1 squared, E1 squared, plus A2 squared, E2 squared, plus A3 squared, E3 squared. And then I assume that the e's are orthonormal, which means that each of the e's has norm 1, right? So this is just A1 squared plus A2 squared plus A3 squared. Okay, so as you can see, what you just do is you just keep on using the Pythagorean theorem, and to make it rigorous, probably the best way to do it is to write it by induction. Okay, so if you have an orthonormal list of vectors, in particular, if you had an orthonormal basis and you found you wrote any other vector as a linear combination, right? So in terms of the basis or in terms of an orthonormal list, then computing the norm is very easy. That's nice. It just depends on the coefficients. Here's another. It's even, let's call it corollary. Every orthonormal list of vectors is linearly independent. And hence, if V is finite dimensional with, let's say the dimension is n, then any list of n orthonormal vectors in V is a basis of V. Okay, so that second part will follow if we can prove the first part, right? Because we already know that if you have any n linearly independent vectors in a vector space of dimension n, they're already a basis. So if we prove that every orthonormal list of vectors is linearly independent, then any n orthonormal list of vectors, list of n orthonormal vectors, is a list of n linearly independent vectors, which is therefore a basis. Okay, so the second statement follows quickly from the first one. So let's prove it. They're linearly independent. And let me just note that this should sort of agree with your geometric intuition, right? Orthogonal vectors, I mean, it's even true for orthogonal vectors, as long as you're non-zero, right? Orthogonal vectors point in different directions. They're perpendicular to one another. They're sort of, everyone points in a new direction, right? In your mind, you should be picturing R2 or R3 or something. So it stands to reason that they should be linearly independent, because that's the same intuition that you have behind linear independence. Of course, we need a proof. So let's suppose that E1 through EM is any orthonormal list of vectors in V. I want to prove that they're linearly independent. How do you prove that a set of vectors is linearly independent? You suppose you have a linear combination which equals 0. You show that all the coefficients must be 0. So suppose I have a linear combination like this equals 0. I want to show that all the scalars are 0. But by the above, we know what the norm of this is. The norm of this, which by the way, it's the norm of the 0 vector, which has norm 0, is just the sum of the squares of the absolute values of the coefficients. So what we have here is each of these is actually a non-negative real number, because the absolute value of a complex number and the absolute value of a real number is a non-negative real number. So what we're doing is we're adding up a bunch of non-negative real numbers and getting 0. This means that each of these is 0. But then the only real or complex number that has absolute value 0 is 0. And therefore, the only linear combination of the e's that gives you the 0 vector is the trivial linear combination. Therefore, they're linearly independent. Okay, so just while we're here, let's define something that shouldn't be a surprise. An orthonormal basis of V is just a basis that's an orthonormal list. Like the standard basis. And again, the point is that a lot of the nice things about the standard basis are true because they're an orthonormal basis, not because they're the particular orthonormal basis that is the standard basis. Okay, so what are some nice properties? Nice properties of an orthonormal basis. Okay, so here's the first nice property. So in general, I'm going to use the letter E here because it's going to be an orthonormal basis in a second. So in general, if this is just any basis of V and W is in V, then we know that there's a unique way to write W as a linear combination of the basis vectors, right? There exist A1 through AN such that W is A1, E1 up through AN, EN. Okay, but in general, if you just take a general basis, it's not that easy to figure out the scalars A1 up through AN, right? In general, not easy to compute. Right, what you would need to do is you need to set up a matrix with the basis vectors as columns. You might need to augment with W, you need to row reduce, and you need to solve for the scalars, which, as you know, is not that fun, right? I guess it's like it's an n-squared algorithm. However, if you have an orthonormal basis, it turns out that it is easy to compute the scalars. So let W be a vector in V, and let E1 through EN be an orthonormal basis. Then, if you write W, we know that there's one and only one way to write W as a linear combination like this, where AJ how do you get the scalar? You just take the inner product of W with EJ. So the scalars that appear in the linear combination, you can get without doing a row reduction. You just take an inner product. Taking an inner product, that's like taking a dot product, right? So that's like n operations. So it's an n, it's order n rather than order n squared. Well, I guess you have to do it n times. Regardless, it's an easy computation to figure out what the scalars are. Furthermore, the length, the norm of W squared is just the norm of each of these inner products squared. Okay, so let me just point out that this last part follows from the first part because of this theorem. This one that we just proved, not this one. This one that we proved before, which is if you have an orthonormal list, then to figure out the norm of a linear combination, you just square all of the absolute values of the scalars and you add them. That's exactly what this is saying, right? To figure out the square of the norm of W, you just take the sum of the squares of the absolute values of the A's, but each of the A's is the inner product of W and EJ. Okay, so it's just a computation. So this is just a computation. Right, so we know that W can be written as some linear combination of the E's. Now let's just take the inner product of that W with this E. Right, so W is like, that's what W is. We take the inner product with EJ. And then we just use the linearity in the first coordinate of the inner product. So you can break up the inner product over the sum. And now most of these terms are 0, right? Because E1 is orthogonal to E2 or EJ, En is orthogonal to EJ. Just in the middle, there's some term that looks like AJ, EJ, comma, EJ. So this whole thing is just AJ, EJ, EJ, which you can now pull out of the first coordinate. But since it's an orthonormal list, the inner product of EJ with itself is 1. And so you do in fact get that the scalar AJ, that coefficient, is just the inner product of W with EJ. Okay, so I said nice properties. I guess I really just mean a nice property. So this is one nice feature of taking an orthonormal basis, which kind of makes sense, right? If you think about the standard basis, I mean, it's a little bit stupid the thing I'm about to say because generally you're given vectors in the standard basis. But if I give you a vector written with respect to that basis, you know exactly what the coordinates are in the standard basis. If I give you just some arbitrary basis, it's sort of hard to figure it out. If you take any orthonormal basis, it is also easy to figure out the coordinates. Okay. So for that and many other reasons, orthonormal bases are very nice, right? But one question you could ask is, how special is an orthonormal basis? In other words, I know that every vector space has a basis. Finite dimensional vector space has a basis. Do I know that every finite dimensional vector space has an orthonormal basis? And even if it's true that every finite dimensional vector space has an orthonormal basis, how do I actually construct an orthonormal basis? Right, so maybe, okay, so orthonormal bases are nice. But the question is, how special are they? Right, by which I mean, does every finite dimensional vector space have an orthonormal basis? If so, how do I find one? Okay, so maybe if you think about Rn, it seems reasonable to expect that maybe you can always find an orthonormal basis. Right? So if you imagine, I don't know, R3 sitting like this, and you take any old vector you want, then it's certainly easy enough to find an orthogonal vector. And then you can look at the plane that these span and then take the normal vector to that. Gosh. Take the normal vector to that. So it seems like, right, in 3 space, you start with any vector you want. It's relatively easy to find an orthonormal. This is like a frame in physics, right? 3 vectors that are orthonormal to each other, no matter sort of how you start with the first vector. So maybe if you use the Euclidean inner product, you can geometrically expect that you can always get an orthonormal basis. And it even seems like you can start with any vector you want, right? I mean, after you've chosen that first vector, let me choose a different color, right? I chose this first vector here. Oh man. I don't know why OneNote doesn't like me sometimes. Sorry about that. Okay. I start with the first vector here. I mean, I even have lots and lots of choices for the second vector, right? Like before I chose this vector, but really if you draw like a circle and 3 space around this vector, I could have chosen any of these vectors as an orthogonal vector. And then you start from those 2 vectors, I guess you only have 2 choices for your last vector. I mean, you have infinitely many choices, but you only have, if you say you wanted it to be unit length, you'd have 2 choices, right? Either following the right-hand rule or not following the right-hand rule. So I should say that for Fn, seems like maybe yes, at least geometrically. Maybe I don't know how to write down the coordinates of an orthonormal basis, but it seems like I should be able to always find one. But remember that there's lots of other inner product spaces that we don't have that much intuition for. For example, we know that the space of, say, polynomials of degree less than or equal to m has an inner product given by you integrate, let me say the inner product of 2 polynomials p and q is you integrate from -1 to 1 p of x q of x with respect to x, and this is some scalar, tells you the inner product of 2 polynomials. Now if I ask, can you get an orthonormal basis with respect to this inner product, I would say you have no idea how to do that, right? Because I don't know what orthogonal polynomials look like with respect to this inner product. I can't picture them like I can in Rn. So I think this question, does every finite dimensional vector space have an orthonormal basis, is a non-obvious one, right? Maybe orthonormal bases are so special that I can't expect them to exist in general. But it turns out, this is linear algebra, everything is nice. So the answer is yes, and there's even an algorithm. What does the algorithm do? The algorithm takes in a basis and spits out an orthonormal basis. It's actually a bit more general even. What it does is it takes any linearly independent list and it spits out an orthonormal list with the same span. It's an algorithm. It's a deterministic process. You can just run the computation. You start with any linearly independent list you want. you take this process, it spits out an orthonormal list that has the same span. It's like just as good as the other one, except it's better because it's orthonormal. Okay, and this is called the Gram-Schmidt procedure, Gram-Schmidt process, Gram-Schmidt algorithm. I think your book calls it the Gram-Schmidt procedure, which is what we'll discuss now. Here's the results. Gram-Schmidt. Suppose that you start with any old linearly independent list you want. What we're going to do is we're going to define one at a time an orthonormal list that has the same span. Okay, so the first vector, we'll call it E1 because it's the start of an orthonormal list. You just take V1. You can sort of start however you want. But I want this to be an orthonormal list. In other words, I want the vectors to have norm 1. And V1 might not have norm 1. So I have to divide through by the norm of V1. Okay, and certainly that vector has the same span as V1. V1, by the way, is definitely not the 0 vector because I assumed it was from a linearly independent list. Okay, what is E2? E2 is you take V2 and you subtract off the inner product of V2 with E1 times E1. Okay. And then this, so the vector that I've just written down, that's going to be orthogonal to E1. It's not so hard to see. I mean, we will see it in the proof why it's orthogonal to E1. But it might not be normal. In other words, it might not have norm 1. So I always just have to divide through by the norm of the thing above. Now it's going to be I mean, the numerator was already orthogonal, but now that I've divided through by the norm, it's going to be length 1. And the last vector is, again, what you do is you take the kth vector in your list, in this case, the last one. And then what you do is you just subtract off the inner product of Vn with every vector on the list times that vector on the list. What you've done is you've taken Vn, you inner product with all the previous ones you've had already. You multiply that scalar by the previous vector, and then of course you still need to divide through by the norm. And that'll guarantee that it's actually a norm 1 vector. Okay, so then E1 up through En is an orthonormal list. And has the same span. Right, so I mean, it's like if I'm in R3 and I look at this plane through the origin, this plane I could write as like the span of, I don't know, this vector and this vector, right? Those are just sort of any two linearly independent vectors on that plane will give you a base of the plane. What the Gram-Schmidt procedure does is it'll return an orthonormal list of vectors that also span the same plane. So what it'll do is I'll take this first vector that I drew and it'll scale it so that it has length 1. And then it will return a vector that's orthogonal to it, that's in the plane that has length 1. So it's like you're taking your linearly independent list of this that determine this plane, and you're scaling them and you're like moving them around on the plane so that they end up orthogonal to one another, but will still span the same space. That's the picture of what's happening. Okay, now let me try to explain exactly what you should imagine is happening here. Okay, right? So at this first stage, it's like you had V1, and instead you scaled it to make it have length 1. Okay, I wonder how well I can draw this picture of what I'm thinking. The answer is probably not that well, but okay, so now at the next stage, you had, right, so our original vectors were, say, like, let's try to draw approximately the same, like V1 and V2, like this. Then we had, this is E1, right? And what you'll do is you'll take V2, but you'll subtract off enough of V1 or of E1 to make it orthogonal, right? So what you'll do is, and then of course you'll scale it, right? So what you do is you subtract off this much of E1, right? That's this bit. You're taking V2 and you're subtracting off this much of E1. That takes you to this vector. And then you scale it. So this will be your second vector. This will be E2. And then at each stage, okay, I mean, and I should point out that maybe if you remember calculus and thought about it hard, this vector that you're subtracting off is really just the projection of V2 onto E1. That's what you're subtracting off. And at each subsequent stage, right, so now we have vectors like this, and it's going to be hard for me to draw in 3 dimensions. But now you have some other vector V3. Imagine this is sort of like pointing out of the screen, but not directly out of the screen. What you'll do is you will, okay, right, so currently these 2 red vectors determine a plane like this, and the blue vector is pointing out, but not necessarily perpendicularly. Essentially what you do is you just project this vector onto this plane, and then you subtract it off. And that vector now will be coming out at a right angle, and then you scale. Okay, so really what's happening here, and I know I haven't drawn it that great, it's sort of hard to draw, is the first vector, you just scale it. Now it's length 1. The second vector, you project onto the first vector. You subtract that off. It turns out that that's going to be orthogonal. And then you scale it. The third vector, what you do is you take it and you project it onto the subspace spanned by the first 2 vectors. That vector will be orthogonal to that whole subspace, that whole plane, and then you scale it. And you just keep on going with this process. And eventually what you'll get is that each of the vectors is orthogonal, and you made sure to divide through by the length, and therefore they'll be orthonormal. Okay, so I think thinking about it this way helps you to not forget what to write down in the Gram-Schmidt algorithm, right? Because there's sort of a lot, like if you look at the last term, it's sort of what the heck is going on. Just think, okay, I'm taking the vector, I'm subtracting off basically the projection onto all the previous vectors, and then I need to remember to divide through by the length. Okay, I'm not going to try to include this picture in the PDF of the notes. So you need to draw this picture and internalize it. Okay, but let's prove that these vectors in fact form an orthonormal list. Okay, so when n equals 1, if you just have one vector, then it's clear that v1 divided by v1 is an orthonormal list. That's a single vector with length 1, it's an orthonormal list. Okay, so suppose that n is greater than 1 and assume by induction that the algorithm works for any collection of n minus 1 vectors. So in other words, I already know that this is an orthonormal list. So that's my base case. And I'm going to assume that the first n minus 1 is an orthonormal list. And I'll prove that this vector en that I've defined is orthogonal to the rest of them and has length 1. Okay, so let me just point out that, okay, so we're assuming that in the thing that we defined, E1 through En minus 1 is an orthonormal list. So we must show that this vector En, which was defined to be, again, you take the nth vector in your list and you subtract off the projection onto the rest of the vectors. And then you divide by the same thing. So let's just say same. Is orthogonal to all the previous ones. Okay, note that this will have length 1 as long as the denominator is non-zero. But the numerator is definitely a non-zero vector because I assumed, okay, so the numerator here is non-zero since Vn was not in the span of the Vn minus 1. That's because I assumed that the list I started with was linearly independent. And by the induction hypothesis, this is the same thing as the span of the e's. Which means that the numerator is definitely not 0, because I can't get Vn just by taking a linear combination of the previous e's. So the numerator is a non-zero vector. I divide through by its norm. It's definitely going to be a norm 1 vector. Okay, so it's clear that, you know, the norm of En is 1. So I just need to show that it's orthogonal. Okay, so now how do I show that it's orthogonal? I just need to take the inner product of these two vectors. Okay, well, what is the inner product of these two vectors? En is Vn minus Vn E1 minus Vn En minus 1. Sorry, I forgot an E1 here. I take the inner product of this vector with Ej, and I divide through by the scalar, which is the norm of this vector, right? So I'll write it once, but then I'm not going to write it again. I'll just right. I'll just call that the denominator from now on. All I've done is I've just rewritten En in terms of the way that we wrote En. Okay, now the inner product is linear in the first coordinate, which means that I can break up this inner product over the subtractions. So you get Vn Ej minus, so that's the first term. It's the inner product of Vn E1 with Ej minus all the way to the inner product of Vn En minus 1 with En minus 1, sorry, times En minus 1 with Ej over the denominator. Right, so there all I've done is I've just broken up the inner product. Okay, but now remember that most of these inner products in this subtraction are 0 because I get to assume that the first n minus 1 of them are orthonormal. So most of these are 0. There's only one term. So this becomes, so this term survives. And then the only term that survives is going to be the EJ term. Right? Divided by the denominator. But now you can pull this scalar out, and then inner product of EJ with itself is just 1. Which means that here you get Vn EJ minus Vn EJ, 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 all of this divided by the denominator. But again, this number is 1. And so what you get is you just get 0. Which shows that En EJ, the inner product, is 0. And so En is orthogonal to all the other vectors on your list. And then also, the first En minus 1 had the span, right? These two spans were the same. That's by hypothesis. But also, if you add En, then you can get Vn, right? Because this is En. If you have En and all the E1 through En minus 1, you can get Vn. Just multiply by the denominator and add to their side. Which means that you can get all of V1 through Vn. So you haven't altered the span. Okay, so the proof is just a computation plus induction. But again, the thing to remember is this picture where you, at each stage, you normalize and then you subtract off the projection and then you normalize. Okay, as a nice corollary, we can actually answer our question, which is every finite dimensional vector space, inner product space. Of course, I require an inner product to talk about orthogonality, has an orthonormal basis. Right? Why? Because every finite dimensional vector space has a basis. Then what you do is you just run it through the Gram-Schmidt procedure. The Gram-Schmidt procedure produces an orthonormal list with the same span. So if you start with a basis, you end up with a basis that happens to be orthonormal. Okay, so the last thing I want to do is I want to try to use, okay, by which I mean, I want to try to use the Gram-Schmidt procedure, but there's just an example in your book where your book goes through it. But I think it's worth it for you to go through it as I talk about it. I mean, none of the computations are particularly hard. But if I were teaching this class in person, I would do it at the board and not just trust you to do it on your own. So let's actually see it in action. So use Gram-Schmidt to find an orthonormal basis of P2R with the inner product that we talked about before, where the inner product of P and Q is the definite integral from -1 to 1 of P of x times Q of x dx. Okay, so this inner product space must have an orthonormal basis, which we should be able to find by using Gram-Schmidt. Okay, so to start, we know that 1x and x squared is a basis of P2R. Okay, it may not be an orthonormal basis. It will actually definitely not be an orthonormal basis if you just take the integral of 1 times x from -1 to 1, sorry, say 1 times x squared from -1 to 1, you won't get 0, which means those two vectors are not orthogonal to one another. Okay, the first two vectors are orthogonal to one another, but not necessarily normal, right? So step 1. What's step 1? You just take the first basis vector divided by the norm of the first basis vector. Okay, so to every normal human being, it seems like the answer to this fraction should be 1. Right? I agree. I'm sorely tempted to write 1 here as well. But note that here, I'm not talking about the number 1, I'm talking about the polynomial 1. And here, I'm not talking about the absolute value of the number 1, I'm talking about the norm of the polynomial 1. So what's the norm of 1? Well, the norm of 1 squared is the inner product of 1 with itself. Let's write it like this, which is the integral from -1 to 1 of 1 times 1, which is 1, dx, which the integral from -1 to 1 of 1, I'm integrating the constant function 1 over an interval length 2. This is just 2. So this means that the norm of 1 is actually the square root of 2. And so show that to one of your normal human friends, and they'll think you're crazy, right? But we're not talking about absolute value of the number 1. We're talking about the norm of the polynomial 1 with respect to this inner product. So this is supposed to be E1. So E1 is the constant polynomial 1 divided by the norm, which is the square root of 2, which your book writes as the square root of 1/2, which is fine. I'll just stick with what your book does. Okay. Now the second step is you take the second vector and you subtract off the inner product of the second vector with the inner product of the second vector with E1 times E1. Okay, so the numerator, and only after that we'll worry about dividing by the length. So the numerator is x minus x E1 E1. Okay, so you always take the next vector in your list and you subtract off things that depend on all the previous e's. Okay, well, what is the inner product of x with E1? It's the integral from -1 to 1. I typo in my notes, let me fix it. Of this vector x times the vector E1, which was the square root of 1/2, dx, that's the inner product, times the vector x. Okay, but maybe the easiest way to see this is that this definite integral, the thing that you're integrating is an odd function. So the integral from -1 to 1 is just 0, right? The integral that you're doing here is some integral that looks like this. You'll get 0. So in the end, this is just x. Okay, in particular, x is orthogonal to 1. But it's not necessarily a length 1 thing. So then you need to know the norm. So what's the norm of x? Well, the norm of x squared is the inner product of x with itself. So it's the integral from -1 to 1 of x squared dx. Right? Oh, I get to do calculus now. This is x cubed over 3 from 1 to -1, which is 2/3. Right, so this means that the norm of x quantity squared is, the norm of x is the square root of 2/3. So E2 is going to be x divided by the square root of 2/3, which your book writes as the square root of 3/2 times x. Which I agree, that's a better way to write it. Okay, third vector. The third vector, again, what you do is you take x squared and you subtract off x squared inner product with E1 times E1 minus x squared inner product with E2, E2. This is the numerator, I should say. After this, we'll have to figure out the norm. Well, what is that? That's x squared minus, okay, well, this inner product is an integral from -1 to 1 of x squared with the first basis vector, which was the square root of 1/2 dx, times the square root of 1/2. Minus, it's this inner product. It's x squared times the second basis vector, which is square root of 3/2 times x, dx times square root of 3 over 2x. Okay, now you can just do these integrals, right? They're not actually that hard, right? Because you're just integrating x squared and x cubed. The scalars you can pull out. So the square root of 1/2 will become, square root of 1/2 times square root of 1/2, that just becomes 1/2. So you should do this. There's too many integrals here for me to do, right? You get x squared minus 1/3. That's the numerator of the thing coming out of the Gram-Schmidt algorithm. I still need to know the norm. Again, the norm squared is the integral from -1 to 1 of x squared minus 1/3 squared dx. It's the integral from -1 to 1. I'll even do this step for you. X to the 4th minus 2/3 x squared plus 1/9 dx. Which, if you do it, is 8 over 45. You get a denominator of 5 when you take the integral of x to the 4th. You get a denominator of 3, of an additional 3 on the x squared term. So you get a denominator of 9. You also have a denominator of 9 on the 1/9 x term. So you get a denominator of 45. Right, so this means that the norm of this vector is the square root of 8 over 45. So you need to divide this vector by its norm. So it's the square root of 45 over 8, x squared minus 1/3. Right, so altogether our orthonormal basis with respect to this inner product is, here's my first basis vector, here's my second basis vector, here's my third basis vector. These are somehow perpendicular in this inner product space, but it's like impossible to see it geometrically. Okay. That computation was not that fun, but hopefully it helps you remember how to compute a Gram-Schmidt orthonormal basis. Note that this is the process that I would actually use if in some problem I actually needed to get an orthonormal basis of something. This is what I would do, right? This isn't just like a theoretical thing. This is like actually the best computational tool if I had to do something by hand like this. So probably I can assign some computational homework problem, or if I don't, you guys should be mature enough at this point to want to do it on your own. You can start with any basis of anything that you want that has an inner product space, and then practice your Gram-Schmidt ting. All right, so as promised, we're going slower through chapter 6. The stuff is just more new. So on, what day is it? Today's Wednesday. On Friday, we'll complete 6B. Then next week, we'll start talking about, believe it or not, 6C. All right.